Today we're going to talk about kinematics, which is the study of motion. And in particular, there's going to be three functions that we're concerned with, and they're all linked together via calculus. The first thing is we have position functions, and typically those position or displacement, it may be labeled as, those are usually going to be labeled as S of t, right? So we have the position function, position or displacement. Ooh, come on. It'll label it as one or the other. It doesn't really matter, but those are typically going to be denoted with an S of t for your position, displacement, or your position S of t. And then we have the derivative of the position, right? If you have, let's say, your position or your displacement, if it's in meters, then your rate of change or your derivative of your position, like meters per second, that would be your velocity. So we also have the velocity functions. That's just the first derivative. And then additionally, we care about more than just the velocity. Sometimes we also deal with acceleration. Something like the units would be meters per second squared. So that's really your second derivative of your position, aka the first derivative of your velocity, or you can just label it as S of t. So we've got these three functions: position, velocity, acceleration. They're all related. Think about position as being like the original function. Velocity is the first derivative. Acceleration is the second derivative, right? Velocity is the rate of change of the position. Acceleration is the rate of change of the velocity. That's really all this first half is telling you about. You can pause it, you can read it if you want. Just kind of make sure you know there's three functions. To get from one to the other, just take the derivative, right? This note is going to be pretty quick, maybe a world record for how fast I go through this in the shortest video, but we're going to try to go through it pretty quickly. Anyways, let us do it. First example. It says the vertical position of a ball thrown from the top of a lighthouse is given by this function S of t. Great. Where S is measured in feet and t is measured in seconds. Find the velocity and the acceleration after 5 seconds. Okay, cool. So this is easy. To find the velocity, we're going to take the derivative, plug in 5. To find the acceleration, we're going to take the derivative again and plug in 5. Of course, always make sure you're watching for your units. So velocity is just the derivative of your position. So using your power rule, that's pretty easy. It looks like a negative 32t plus 96. And then specifically then, the velocity at time equals 5. 32 times 5 plus 96. Let's see, I think that's going to end up being negative 64 feet per second, I believe. So there's your velocity at time equals 5 seconds. Your velocity formula as a whole is given by this, just the first derivative, and then specifically 5 seconds, so when t equals 5. Okay, that's great. Let's go get the acceleration, which is just your derivative of your position, which is also known as the second derivative of your acceleration or of your position. So let's see, the derivative of this function would just be negative 32. And so your acceleration at time equals 5 is going to be negative 32 feet per second squared. Or if you want to, feet second squared. I know in IB they like to write times with the negative 2 exponent as opposed to writing over the time unit squared. It doesn't matter. It's the same thing. And I think that is the gravitational constant if you convert it to feet per second. I believe it is negative 32. Whereas if you were in meters per second, it's like 9.8 or whatever. And a lot of times they'll just round it to 10. Okay, very nice. Let us look at the next example then. A rocket is launched upwards into the air. Its vertical position, again, given by this function, S of t. Now units are in meters and in seconds. Always watch out for your units. Find the average velocity from the time interval 1 to 2. So this really doesn't have anything to do with the derivative, right? Your average velocity, that's just your secant slope. So that's going to be your change in your position over your change in time, and specifically we want from 1 to 2. So this, you're just going to do the position at 2 minus the position at 1, right? You need to figure out how far does it travel. So the final position minus the initial position, and then over 2 minus 1, your final time minus your initial time. So average is still the secant slope. That's asking over the interval. What's that speed going to be? So you just plug 2 in to this function, plug in 1 to this function, and then divide it Really, you don't have to divide it by anything because it would be divided by 1. So if you were to do all that calculations, if you plug in 2 to this function and then subtract the plugging in of 1, I believe you should get 3 meters per second. Wonderful. Let's look at the part B. Find the instantaneous velocity. Okay, so there's the derivative, and it says evaluate it at time equals 1. All right, so my velocity is just your derivative of your position. And so that looks like, here it is, it looks like it's negative 10t plus 18. And then specifically at time equals 1, negative 10 times 1 plus 18. It looks like it's 8 meters per second. Okay, so we did this average velocity, no calculus involved. We did this very minimal amount of calculus involved. You're just taking the derivative. And now we're already on part C. Find the maximum height reached by the rocket, and then find the time at which this occurs. My pencil head just is not working today. I am sorry. Okay, so here we go. If we have a calculator, we obviously could just graph this sucker. So let us do it. Let me get out my calculator. Let's go for it. By the way, if you wanted to, you could use the calculator. I don't remember if I've shown you this. So, sorry, batteries. Go away. Let's go ahead and type in that position function. So it's a negative 5x squared plus 18x plus 1. All right, wonderful. If you wanted to do, obviously, let's just go back and check part A. So we have vars, y vars, and then we had 2 minus... Oh, no, I must have something typed in wrong. Yes, I know. Oh, that's why. I had the minus sign instead of the negative sign. Okay, at least now I got it graphed right. So cool. Let me go snag this, do it again. There we go. We got 3. So yeah, definitely make sure you use the negative sign for that leading coefficient as opposed to the minus. That was silly. But we confirmed that we got the average speed. That was great. Now, if you wanted to do the derivative in the calculator, you can. Let's clear that. You just hit math. And then if you scroll down, like, hey, that's going to find the minimum. That's going to find the maximum. Derivative, math 8. That is how you can do derivatives in the calculator, math 8. So we hit in derivative. Always type in x because that's the variable we're working with. You would type in your function, or if you already have it function typed in, you just got to go snag it from y1. And then here specifically, I wanted to find the speed at time equals 1. Right, so you can do derivatives in the calculator. It's via that Math 8 feature. Of course, you would still probably want to show work, but you can use the calculator to check. That's really nice. Again, you just hit Math 8, and then this should always be the variable x. Here you would either type in your position function, what you want to take the derivative of, and then you have to tell that little evaluation bar where do you want the derivative. The drawback behind the TI-84s is it can't tell you the whole derivative function, right? The calculator, at least the 84s, they cannot give you a function as the answer. It can only give you a numerical value. So it can't tell you the whole derivative function, but it can tell you the derivative at one specific point in time. Okay, if you have an 89 or if you have like a Casio, one of those nicer calculators, I believe it can give you the whole function, but you should be able to do the calculus by hand anyways. All right, so part C, let's go to it. It says find the maximum height reached by the rocket and the time at which this occurs. So we're going to use the calculator. And so what we're going to do, of course, anytime you use the calculator, you would want to make sure you write a note on your paper that's indicating what you're doing with the calculator. You shouldn't just have these numbers appear from nowhere. You should really try to make sure you're doing something to justify your work. So you could say use GDC, that stands for Graphing Data Calculator. Use GDC to graph S of t and find the maximum. Okay, so that's one way to do it. If you had a calculator, you could just graph it. It looks like it goes up too high, so I'm going to restrict this domain. I don't need it to be negative time. I do need it to be a little bit taller, though. So there's your function. Again, we don't really care about what happens after it hits. We just wanted to find the maximum height. So we graphed it. I'm going to second trace because I want to calculate, and I want to find the maximum. Left bound, so you got to click somewhere on the left. Or you could just type in like 1. It'll work. And then right bound, you could type in something like 3, or you can scroll if you want. The guess doesn't really matter. You can scroll and get closer to the guess, but whatever. And then here it looks like that maximum is going to be 17.2 meters when t equals 1.8 seconds. So here we could say max height is 17.2 meters when t equals, was it 1.8, I think? 1.8 seconds. So we could get everything just from the calculator. It's really nice. You literally just graph it, trace the maximum, super quick, super easy. If you wanted to actually do calculus to justify the answer, we could. We know how to find maximums and minimums, right? We would just use the first derivative to figure out when it changes from positive to negative, so on and so forth, right? So if we wanted to do calculus to really do this part C, which we could do a sign chart for S prime. Remember, S prime is just the same thing as the velocity. Now here we go. Let's see. Where is my velocity? There it is, the negative 10t. So you have your velocity is negative 10t plus 18. So if you set that equal to 0, you're going to get 18 over 10. So 9/5. Right, so 9/5 is your critical point. That is where the derivative, the velocity, is going to be equal to 0. If you were to test it, if you were to plug in something like 2, which is bigger than 9/5, negative 10 times 2 would be negative 20, negative 20 plus 18. Oh, so that's negative. So your function is decreasing. Then if you plugged in something like 1, you'd have negative 10 plus 18, so that's positive. So you could do this sign chart to confirm that yes, you are going to have a maximum at this time, which is 1.8. And then you could always just take this value and then take this 9/5 or take the 1.8 and then just go plug it back into that original function. And then it would tell you what that maximum height is, right? So if you did the calculus way, you would just need to do your function evaluation, plug it in at your 9/5, not 9.5. I caught it that time. That was nice. And then it'll tell you, hey, that maximum height, right, the y-coordinate was 17.2. So for something like this, I would probably hope that you could show some calculus work. If you have a calculator, sure, like it's going to be fine if you use the calculator, as long as you write a little note explaining what you did with the calculator. If you just have this stuff magically appear, then you're probably not going to get all the points. You have to kind of explain where it's coming from. But if you have a calculator, you could use the calculator. If you didn't, you could do it by hand. We know how to find the max. You just do that first derivative sign chart, and specifically, it's going to have to change from positive to negative. So a couple different ways to do that. But yes, we did find the maximum height and the time value that it occurs at. All right, flip it over to the back. We got the last example, 5.3. An object moves along a straight line so that after t seconds, its displacement. So here instead of the vertical position, it says displacement. That's okay. The displacement is given by this function s of t. Part A is just find the velocity and the acceleration. That's easy. Find the two derivatives. Part B, find the initial velocity. So plug in 0 to the velocity and the initial acceleration. Plug in 0. And then part C is find the maximum displacement and the maximum velocity. Okay, so let's do this. Parts A and B are super quick. I was totally all the way off the screen. I would be surprised, but I've just been, really bad with the videos the last 48 hours. Oh well, we'll live. Part A, the velocity is your first derivative of your position. So that is smelling like a negative 6t squared plus 6t, right? And then I guess we could put units on it. It would be meters per second because your distance is in meters and then time is in seconds. And then here we go. That was I. Always label your sections, right? Whenever you're working on an IB question, you have like 20 million parts. Make sure you label it. Like here's part A, here's AI, here's AII. Make sure everything is labeled and neat and organized so that your graders, me and the IB graders at the end of the year, they don't have to hunt for your work. Anyways, acceleration, that's your derivative of your velocity, aka the second derivative of the position. No, you don't really have to write this as long as you have the correct answer. They'd be fine. But here, take the derivative again. You get negative 12t plus 6, and then your units would be meters per second squared, right? Or meters per second to the negative second power. Okay, so part A, done, done. Always make sure you answer all parts of the question. Now let's do part B, which is just plug in 0. So velocity at 0. That one's easy. 0 meters per second. And then I, your initial acceleration. Just plug in 0 to this. Negative 12 times 0 plus 6 looks like 6 meters per second squared. So the A and the B is really pretty easy. Really, I think I messed up somewhere, didn't I? Let's see. Let me find it. What's the derivative of 6t squared, right? I don't want to remake the whole video, so we're just going to fix it. The derivative of 6t squared isn't 6t, it's 12t. Hope you caught that earlier. I totally didn't, hence me going back and fixing it now. But that should have been a 12t, which means this would have been a 12, which means this was a 12, and that was a 12. Okay, oops, sorry. I guess this one would be 12 times 0 too, if you want to fix it. Doesn't really matter since it's still 0. But yes, the derivative of this, let's check. That looks like negative 6t squared, and then plus 12t. There we go. So that's the correct velocity. So then that's the correct acceleration, and then you just plug in 0, and then there are your values. Okay, but we got the initial velocity and the initial acceleration, so the part B is totally done. Now we got the part C, which says find the maximum displacement and the maximum velocity. Again, you could go ahead and use the calculator to graph them, and then you could just use the calculator to find the max. That's pretty easy. Let's try to do it without the calculator as best as possible, because that paper 1 IB exam, you don't have a calculator, so you got to be able to do stuff by hand quite a bit of the time. All right, let's go through and let's find the max displacement. Okay, to find max displacement, we are going to need the velocity equal to 0, and then specifically, you're going to need it to change from positive to negative, right? You're finding that derivative sign chart, and then you're specifically going to have to confirm that it changes from positive to negative. So let's go for it. Let's do this sign chart stuff for your velocity. So your velocity was negative 6t squared plus 12t. We want that to be 0. Factor out a 6 and a t and the negative. And we have t minus 2. So it looks like t equals 0 and t equals 2. Those are your critical points. Obviously, we're not really going to care about this, right? We know the velocity at time equals 0. It's 0, so that one doesn't help. But let's go ahead and just do the sign chart for us. Just to make sure. So here's your velocity, time equals 0, time equals 2. There were your two critical points. Let's test it. If I plug in something between 0 and 2, like 1, let's see. This chunk would all be negative, because it would be negative 6 times 1. So that's all negative. That would be negative. But that means overall it would be positive. And then anything bigger than 2, like 5, let's see, you'd have a negative 30, and then that would be a positive 3, so overall it's going to be negative. So look, we did confirm that 2 is indeed going to be a relative maximum, right? So we'd want to make sure, right? Just because we know it's a critical point doesn't guarantee that it's a max or min. You still have to decide what type of a critical point. Is it a max or a min or neither? How does it change? So you should still be doing your sign chart to confirm that it changes in the correct order. But of course, it probably will. Okay, so now we still need to answer, because it doesn't ask what's the time value where you have the max displacement. It says what is the max displacement. So I'd still have to take this 2 and plug it back in to the original position function. So I'd have negative 2 cubed plus 6 squared. So let's see, that's going to be negative 16 plus 24. So it looks like that maximum displacement is going to end up being 8. Okay, so that was good. We got the part I done on C. Let's now do II. To find the maximum velocity, we're going to need the derivative of the velocity, aka the acceleration, to be 0 and change from positive to negative. Right? So anytime you're looking for a max or a min of blank, you need to take blank's derivative, make sure it's 0, and then make sure it changes from positive to negative at the spot where it is 0. So if you're going to find the max position, you would actually set the velocity equal to 0. And then if you were to find the max velocity, you would set the acceleration equal to 0. Or if you're trying to find the max acceleration, Well, you would take the derivative of the acceleration, which is called the jerk, but you would take the derivative of the acceleration, set it equal to 0, and then do your sign chart. And specifically, you'd have to confirm that it changes in the correct order. But anytime you're trying to find a max or min, you always take a derivative of that thing, and then set it equal to 0, and then do your sign chart work. Okay, but here we go. Acceleration function, we already had it. It was negative 12t plus 12, set it equal to 0. So I'm thinking we're going to get time is going to be equal to 1. Always label your sign charts too, so that way your work is organized. All right, if I plugged in something like 5, you're going to get a negative value. So your acceleration or your velocity would be decreasing. Remember, we're using the acceleration to answer questions about the velocity. Here we were using the velocity to answer questions about the position. If I plugged in something like 0.5 or 0, you could use 0, it looks like your value is going to be positive. So it does look like we indeed confirmed 1 is the time value that's going to maximize the velocity. And then to actually figure out what that maximum velocity is, look, it even told us just on the interval 0 to 3. We didn't really care because all of our critical points were between 0 and 3. But now we actually still need to figure out what that maximum velocity is. So I'd take 1 and plug it in to your velocity equation. So we'd have negative 6. Where's my velocity? There it is. 1 squared plus 12 times 1. So negative 6 plus 12. So it looks like 6 meters per second. So pretty nice, lots of stuff going on with this kinematics, but really it's not too bad. Now it's just kind of extending the ideas that we've been doing the derivative and then doing that first derivative sign chart. But now we know if I have a position or a displacement, the first derivative is the velocity, and then the second derivative, which is the derivative of the velocity, that second derivative is the acceleration. And then if you want to maximize anything, you would take that thing's derivative, set it equal to 0, and then do your sign chart. Make sure if it's a max, it changes from positive to negative. If it was a min, it would have to change from negative to positive. And then if the derivative doesn't change, then it would be neither a max nor a min. And of course, if you had a calculator, you could always just graph it in the calculator and then use the calculator to find the max or the min.